Hello dear students. So in the last class we had discussed the wave propagation in lossy dielectric, and for the lossy dielectric we had seen the expressions for alpha and beta. Okay, so that you can see. Now thereafter we had considered the three cases. Okay, so the three cases were, we considered first the lossless dielectric, okay, in which the sigma is very much less than omega epsilon. Okay, sigma is 0, epsilon equals to epsilon 0 epsilon r, and mu equals to mu 0 mu r. Okay, then alpha equal to 0 and beta equal to omega root over mu epsilon. Okay, so this case we had discussed. Okay, thereafter we had discussed the case 2, that is in free space we have this sigma equal to 0, epsilon equal to epsilon 0, and mu equals to mu 0. Okay, so then if we will put these conditions in alpha and beta, then we will get alpha equals to 0 and beta equals to omega root over mu 0 epsilon 0 equals to omega upon c, where c is the velocity of light. And the third case we had considered was in a good conductor. Okay, so we know that the perfect or good conductor is one in which the sigma is very much greater than omega epsilon, so that the sigma upon omega epsilon is greater than or very much larger than 1. Okay, so for perfect conductor, sigma is what it is, the conductivity will be infinite. Okay, because we are considering the, however it is not practically possible, but if we are considering a theoretical perfect conductor, then we will have to consider this condition. So sigma equals to infinity, epsilon equals to epsilon 0, mu equals to mu 0 mu r. So alpha equals to beta in that case, and that will be equal to root over omega mu sigma upon 2. So these cases or conditions, okay, for the wave propagation in different types of medium we have seen. Okay, now we will proceed towards the next topic. So the next topic of discussion is the skin depth, because at this point of time we need to discuss, now we can discuss this. So it is the skin depth. Okay, now what is skin depth? So the skin depth is a measure of the depth to which an EM wave can penetrate the medium. Okay, so what is this topic, what is the definition of this skin depth? So the skin depth is a measure of the depth to which an electromagnetic wave, that is EM wave, can penetrate the medium. Okay, so this is represented by delta, and delta equals to 1 upon alpha. Okay, so in a medium of high conductivity, the wave is attenuated as it propagates due to losses which occur in the medium. Okay, so we can consider some points that in a medium of high conductivity, so we are considering such mediums in which the conductivity is very high. Okay, so in a medium of high conductivity, the wave is attenuated as it propagates as it propagates due to the losses which occur in the medium. Which occur in the medium. Okay. So what we can say that in a good conductor, the rate of attenuation is very great and the wave may penetrate only a short distance before being reduced to a negligible small percentage of its original strength. Okay. So the next conclusion we can draw, is that in a good conductor, the rate of attenuation is very large or is great, you can say, and the wave may penetrate and the wave may penetrate only a very short distance, only a very short distance before being reduced to a negligible small percentage of its original strength. Its original strength. Okay. So these are the conclusions which we can draw from this skin depth. Okay. So what we actually observe that in a good conductor, the rate of attenuation means, I will show it with the diagram, that the strength is being reduced. Okay. So the rate of attenuation is large and the wave may penetrate only very short distance before being reduced to a negligible a small percentage of its original strength. Okay. So that we can see with the help of diagram that let this be your x-axis, so we can make it like this. Okay. So here you can see that the amplitude is decreasing, it is going to be attenuated. Okay. So at this point, if we talk about at this point, so the amplitude has decreased. Okay. And let's say this is E0, then this one is your 0.36 8E0. So it has reduced to up to 36.8%, you can see. Okay. So if we consider E equals to E0 e to the power minus alpha x, okay, cos, and it is the function of time and space. We can write omega t minus beta z and the component along az. Okay, so the amplitude of the wave decreases by a factor e to the power minus. So what is the observation here, that the amplitude of the wave, we can see this wave, the amplitude is decreasing. Okay, so amplitude of the wave decreases by a factor e to the power minus alpha x. Okay, where alpha is what? Alpha is the attenuation constant. Attenuation constant. So if you observe this graph, you can observe that it is the what, varying like e to the power minus alpha x, because if you see the graph of e to the power x, then you will get the idea that the amplitude is decreasing by the factor e to the power minus alpha x. Okay, so as the amplitude is decreasing by the factor e to the power minus alpha x, and alpha is what? Attenuation constant. So we have seen this relation. Delta equals to 1 upon alpha. I am talking about this. So delta equal to 1 upon alpha. So alpha is the attenuation constant. Okay. So if we remember, what is your alpha? So just now we were discussing the alpha. So alpha, let me remind you what was your alpha and beta. So alpha was your omega root over of mu epsilon upon 2 inside bracket 1 plus omega square upon omega square epsilon square. Okay, minus 1. Now since your delta is what? Delta is 1 upon alpha. Okay, so the skin depth, delta is given by 1 upon omega root mu epsilon upon 2. Here it was root mu epsilon upon 2 root over of this 1 plus sigma square omega square epsilon square minus 1. Okay, so this is your delta. Now we know that for a good conductor, your sigma upon omega epsilon will be very much greater than 1. So in that case your delta will be what? Delta will be 1 upon alpha, that is we know. So it will be somewhat equal to root over of 2 upon omega mu sigma. Okay, and if we will put the value of this omega, okay, that is 2 pi f. So if you will put the value of omega, then 2 and 2 will be cancelled out, so it will be 1 upon pi f mu sigma. So this is the value of skin depth. Okay, now for copper it has been calculated that for copper with conductivity, its conductivity sigma equals to 5.8 into 10 to the power 7, mu equals to mu 0 at f equals to 1 megahertz. Okay, your delta is coming out to be, if we put these values and then we calculate delta, delta is 0.0661 mm. Okay, so for copper with conductivity and all these conditions, if you put, then delta equal to this. So the sample value, sorry, the same value of delta, because we use copper conductor as our for our electricity transmission at 50 hertz. So if we calculate the same value of delta at 50 hertz frequency, okay, then your delta will be equal to 9.35 mm. Okay, so all fields in a good conductor such as copper are essentially zero at distances greater than a few skin depths from the surface. Okay, and electromagnetic energy is not transmitted in the interior of the conductor. It travels in the region surrounding the conductor while the conductor guides the waves. Okay, so this is the fact actually we should understand, or we should keep in mind also, that all fields, whether you talk of electric or magnetic, all fields in a good conductor such as copper. Okay, copper is certainly considered as a good conductor. So all fields in a good conductor such as copper are essentially zero. So fields are zero. Okay, essentially zero at distances at distances greater than a few skin depths from the surface. Okay, and at the same time you will have to consider that the electromagnetic energy is not transmitted in the interior of the conductor. Okay, it travels in the region surrounding the conductor while the conductor guides the waves. Okay, so this is also a point which you need to remember, that electromagnetic energy is not transmitted in the interior of the conductor. It travels in the region surrounding the conductor. Okay, and the conductor guides the waves. Okay, so these are the points, and the next topic of discussion, this is all about for the today's discussion, and for the next topic of discussion will be reflection of the uniform waves by perfect dielectric normal incidence. So we will see the reflection of the waves topic. Okay, so when the plane wave is incident normally on the surface of perfect dielectric, then some part is reflected. Okay, and if the dielectric is perfect, so what are the conditions and what will be the propagation uh, conditions? So that we will discuss in the next class.